Hello, and welcome to today's webinar. Explain your ML models with Amazon SageMaker Clarify. Before we get started, I have a few quick housekeeping items. On the left side of your screen, you will see a Q&A pod. Please submit your questions for our presenter and moderators at any time, and we will address them while they come in. At the end of today's presentation, we'll answer poll questions during Q&A. Please send us your feedback when you see these poll questions appear on your screen. Today's webinar is being recorded. In the next few days, we will send you a follow-up email with the on-demand links to the slide deck and webinar recording. Again, welcome to today's webinar. Explain your ML models with Amazon SageMaker Clarify. Today's speaker is Dr. Dennis V. Batiloff. Welcome. The floor is now yours.
Well, hello and welcome to my talk on explaining your machine learning models with Amazon SageMaker Clarify. My name is Dennis Batiloff, and I'm a worldwide tech leader for AI/ML at AWS. I do have a PhD in machine learning as well, and you can follow me on Twitter at the handle indicated. So we're going to talk today about a very important topic of responsible AI and specifically focus on explainability. So let me start by giving you a quick agenda for today. So from the responsible AI, we'll move on to explainability, the actual challenges and the principles behind that. And I will give you an explanation, pun intended, of SHAP, which is an algorithm that's underpinning the explainability functionality in Amazon SageMaker Clarify. Of course, we will do a demo, and time permitting, we'll have time for your questions. So please drop them in the chat during the session. So making sure AI is done responsibly is ultimately a multidisciplinary problem that needs to draw from the fields of moral philosophy, economics, there's always a cost-benefit trade-off, and then law, social science, and of course, technology. At AWS, we're committed to the responsible use of AI, and it is a priority not only for us, but for our customers. We help customers look at their machine learning holistically. In other words, looking at what needs to be done to align people, processes, and technology to drive better outcomes and to reduce risk. And speaking of risk, there's lots of different considerations here, starting from reputational damage, revenue loss, and of course, regulatory backlash, all the way down to possible criminal consequences. So no wonder that we need to take this very seriously. And we can aggregate many different questions and concerns around responsible AI into the 7 pillars you see on the screen. For example, you may care about the carbon footprint of machine learning models, and this naturally falls into the accountability pillar. Whereas dealing with deepfakes likely falls under data, personal privacy, and protection. In today's talk, we're going to look at the tools that are currently offered by Amazon SageMaker Clarify, which primarily cover fairness and explainability pillars. Being able to detect unwanted bias and build fairness into the AI decisions is a key area that SageMaker Clarify can help you with. But in today's talk, we will focus on explainability specifically. So what do we mean by explainability? We start with a why. Why do we need model explainability? Even before the model is put into production, we often need to debug the model or improve its performance. And explainability is often defined as a way for humans to build a mental model, pun intended in this case, of how the machine learning model functions. If such a mental model is good, the chance of the machine learning model predictions to surprise us is thus low. And that helps with a common second reason, namely the need to build trust in our model. There's a great parallel with software development generally. The more we debug and test software, the higher is our level of trust. And so it is with machine learning. But there also needs to meet regulatory requirements for the model and audit past decisions. And finally, we need to support human decision making. For example, if the machine learning model is showing the customer service agent the prediction of why this particular customer is calling now, it helps for the machine learning model to display an explanation so that the agent can choose to accept this prediction or ignore the possibly erroneous automated assistance. Okay, so how does SageMaker fit into this picture? Now, this talk is not about SageMaker functionality in general. The expectation is that you probably know about SageMaker, but just to give you a high-level overview, SageMaker handles these key steps in any machine learning model lifecycle. One needs to start with collecting and preparing data, for example, by using SageMaker Data Wrangler, and possibly labeling it first with SageMaker Ground Truth. Then the model needs to be developed, trained, and tuned where SageMaker Studio, SageMaker Experiments, and training can all help. And finally, the model needs to be deployed and monitored with SageMaker Inference and Model Monitor. Now, SageMaker Clarify is the tool that is designed to analyze your data and model for bias as well as explainability, and then ultimately helping you monitor the drift in model in both bias and feature attributions, which we will shortly see from the foundation of explainability. All right, so what you see on your screen is a list of functionality that Amazon SageMaker Clarify supports. I mentioned bias. We talked a little bit about drift, but really in this talk, we will zero in explainability both at the global and local level. We'll talk about the distinction here, and we'll cover the kind of newer modalities that SageMaker Clarify supports in terms of explainability, such as images for computer vision and text for natural language processing. So let's jump into explainability. First of all, if you see a machine learning model that is fairly simple, let's look at a single decision tree, for example, then the reason why this model produced a particular prediction is very easy to understand. We just need to trace this decision from the root of the node all the way to the leaf, looking at the different thresholds that are applied. And in a way, that forms an explanation. Effectively, it's a kind of a set of if-then clauses, and it feels fairly self-explanatory in that sense. But even with a single decision tree, there's still a question looming as to, well, why is this specific threshold chosen? Right? It's not quite clear. And a simple decision tree is rarely what we ever put into production nowadays. Even if you choose the tree-based algorithms, we typically work with an ensemble technique. So it's either a random forest, or you have some boosted trees. And in any case, you have many trees of different depths, and it becomes already harder to interpret and explain what is going on. And now consider the case of neural networks. What you see on the picture looks quite complicated, but as far as the neural networks go, this is actually a very simple one. In fact, if we consider the more recent, well-publicized neural networks such as GPT-3, those have 175 billion parameters. And in fact, more recent ones have measured in several trillion parameters. So seems like it's a very, very hard problem, and maybe even untractable problem when we look at it this way. To give you a quick summary of the apparent trade-off between the accuracy and explainability, you could see that if we start with simpler methods such as linear models, where we have a hyperplane as a decision boundary, and maybe in some simple cases really literally as a single line. So if your point is above the line, then we predict it to belong to one class, and if it's below, then it's the other class. So in some ways, it's a simple thresholding mechanism, and again, feels like it's self-explanatory. But as we move on to more and more sophisticated models, especially going to neural networks, then while the accuracy is improved due to the sophistication that's necessary, the explainability suffers dramatically. So is all hope lost? Well, as it turns out, there is a way to solve it, and this approach comes from the game theory space. Specifically, we call this a feature attribution problem because we're trying to understand the relationship between the input feature values and the resulting prediction. So for example, if we have a lending model, then we want to attribute its prediction of whether to underwrite the loan or not to the different inputs that went into it, such as your credit score, your income, and maybe other parameters. If we talk about different modalities such as object recognition or text sentiment, then again, we need to attribute the predictions to the corresponding inputs. In the computer vision case, these are pixels. We'll actually see how to do this and not just look at the individual pixels. But in case of natural language processing, it's words and phrases and sentences. So in general, whatever modality we're dealing with, that attribution is going to come out in terms of the features that go in. And the interesting thing about this approach is that we can treat the model as effectively being opaque. And that's an additional bonus because then that technique does not rely on any specifics of the model. And this works well for SageMaker, especially since it's a platform that's designed to support all kinds of models and frameworks to be used. Okay, so what do we mean by game theoretical result? Specifically, I'm talking about Shapley values. And Shapley values were invented by Lloyd Shapley, who actually received a Nobel Prize for this work. And the problem is stated as the need to fairly distribute the payoff from a cooperative game played by a so-called coalition of players. So just as we're trying to figure out the marginal contribution of each player to determine the fair split of the payoff, later in machine learning, we will be using a similar approach to figure out the marginal contributions of various features that resulted in a particular model prediction. So consider the following scenario. Let's say there are three friends, Alice, Bob, and Carol, and they want to get from, let's say, a party back to their respective homes. So for Alice, that taxi ride will cost $6. For Bob, it's 11, and Carol lives a little bit further out, so for her, it's 15. So if each one of them take the individual taxis, then the overall cost will be $32. But of course, they can also choose to share a ride. And if they do so, then the overall cost will only be $18. And the way it's likely going to happen with, say, friends is that, Alice will get off at her place first and pay the $6 of the fare up to now. Then Bob will pay off the fare from Alice's place to his, and Carol likewise will pay the fare that results from the trip from Bob to Carol. And in this case, in this scenario, we assume that all of them are even at $6. Okay, that's how likely it's going to play out. But if we think a little bit about it, it's not exactly fair, because Alice, in this case, is paying the same $6 she would have paid if she took the ride by herself, whereas clearly Bob and Carol are benefiting from this shared ride somewhat. So perhaps our intuition tells us that Alice, in a fair distribution, should pay less than $6. And likewise, maybe Bob should pay a little bit less, because Carol is benefiting from the fact that Bob is paying for the ride up to his place. And in fact, if we apply the Shapley values approach, we will discover that the fair distribution, according to Shapley, is going to be as follows. So Alice should actually pay $283, Bob should pay $533, and Carol should pay $983. And I know there's a cent missing here, so somebody will pay an extra cent in the process. And maybe that feels a little bit surprising to you, but let's actually look at how this is done. And by the way, you could also see a more detailed description at the Coursera lecture that I mentioned in the link below. Okay, so let's look at this a little bit more carefully. We need to consider the different orders in which these coalitions of Alice, Bob, and Carol are formed, and the way the marginal contributions are evaluated, and the overall payoff and the individual pays or costs are computed. So let's start with the coalition where Alice joins the so-called empty coalition first, right? In this case, well, that's going to be just a simple ride to her place, and she is committed to paying $6 to it. And now Bob comes along, and Bob can actually benefit from that trip up to Alice's place and needs to just pay the additional $6, because the total coalition of Alice and Bob, the most optimal ride for them, is $12. And now C comes along, or Carol, and Carol also pays $6 for the same reasons. And so far, this is exactly like we discussed just previously. But let's look at a different ordering. And pay attention, because things here become a little bit more complicated. So if Alice adds or joins the coalition, the empty coalition, again, it's the same as before. So she commits to paying $6. But now let's say instead of Bob, it's Carol who joins the coalition. Well, for that joint coalition of Alice and Carol, this is the actual optimal route. And we're assuming here that, again, the trip from Alice to Carol is going to cost $11. So together, they will pay $17. And since Alice has already committed to paying $6, Carol just needs to contribute the difference, which is $11. Okay, so far so good. Then Bob joins the coalition, and all of a sudden, the optimal route goes back to that original one. But because Alice and Carol have already committed $17 total, and the joint resulting coalition cost is going to be $18, Bob just needs to pay the difference, which is $1. Okay, so let's start with Bob now. So Bob joins the coalition first, and the trip to his place directly is $11. Again, another assumption here. And so he's committing to $11. Then Alice joins, and again, the optimal route, instead of $11 for just Bob, the optimal route for them together is going to be $12. Right? So since Bob has already committed 11, Alice needs to just pay the additional $1. And now Carol joins the coalition. So far, $12 have already been committed to it. And out of the $18 total, Carol just needs to pay the difference, which is $6. If we do it for the other orderings, we get something like this. And again, let's just look at the last one in a little bit more detail. So in this case, Carol joins the coalition first. She commits to $15. And then we have Bob joining. So now the most optimal route for both Bob and Carol is 11 and 6. So Bob now needs to only pay $2 additional because 11 plus 6 is 17, but Carol already committed 15 out of those 17. So Bob's additional contribution needs to be $2. And then when Alice joins last, we go back to that original optimal coalition that is $18 in cost. But since $17 have already been paid by the two other parties, Alice's additional cost is just $1. And here we see the marginal contributions depending on the different orders in which the coalitions are formed. And so now if we average out these marginal contributions, we will arrive exactly at the values that were shown previously. So hopefully this gives you some insight as to what's going on with Shapley values and game theory. But now we need to translate that to machine learning, and we need to look at SHAP algorithm. So here's how we can think about this translation. And on the next slide, I'll show you, a formula of sorts, if you wish. And we need to understand how that translation works. So whatever used to be the game payoff in the game theory becomes the model prediction in machine learning. And whatever were the players whose marginal contribution we wanted to compute now become features, because in explainability, we want to understand to what degree each of the input features contribute to the ultimate prediction. So naturally, a subset of players translates to a subset of features. A specific player is really a specific feature. And then we're going to be talking, of course, about explaining individual game instance or individual machine learning instances. But the translation to the game theory is a game instance in a way. So remember our coalition of Alice, Bob, and Carol. Well, the players could be the same, but I could easily change the conditions of this game by changing the actual costs involved, right? So Alice wouldn't pay 6, she would, let's say, pay $20 for her ride. And I can change all the different costs and end up with a different version of that game instance, which will, of course, change the computation somewhat. All right. So, by the way, this SHAP algorithm was due to Scott Lundberg and others, and this was originally published at NeurIPS in 2017. So again, amazing how quick we take something from kind of applied science and immediately translate it into use. So for the algorithm now, SHAP stands for Shapley Additive Explanations. And the way to interpret what you see on the screen is, remember that the f of s is the prediction based on a subset of features. Now, what do I mean by a subset here? Is in any kind of machine learning model, we need to feed in likely all the features or all the feature values that we have available. Well, in this case, the idea is that there should be a way to provide only a subset of features. So we can look at, let's say, a coalition of Alice and Carol, not the overall coalition. Now, in machine learning, what that means is that you may need to be able to feed a missing feature into the machine learning model. And not all models play well with this idea. So in cases where this doesn't work, what we really need to do is provide some sort of baseline value instead of the feature that we want to kind of exclude from the coalition. And what we typically do is we provide the value in that baseline that has sort of the least kind of interesting amount in there, in the sense that it's the least surprising, it's the most common maybe. So one typical approach is to just compute the average across all of your training data set for that particular feature and treat that as the baseline value. So then, according to this approach, what we're going to do is compare the difference, or calculate the difference of the prediction of feeding in the subset of features together with the feature that we care about, which is I, and getting the prediction without that feature I. And so having that difference, again, gives us the marginal contribution of that feature, and then we need to average this over all the different possible orderings of the subsets of features that are out there. And if the number of elements in your set is 3, like with Alice, Bob, and Carol, well, that's not so hard because we only have 6 different orderings. But in theory, you could have thousands of features passed into kind of a modern machine learning model, and as a result, it would take exponential time to actually compute these aggregate marginal contributions. So another contribution of this algorithm is the idea that instead of computing the exact attribution of a feature, we will instead approximate it. And we use it with kernel functions. And so hence, this algorithm is also commonly referred to as kernel SHAP. And there are some approaches here that choose a particular number of samples that are used instead of the full range of possible coalitions. And then we've talked already about the way of replacing the missing values with some baseline values. Okay, so let's look at a specific example. And in this case, I want to mention this exciting kind of development or application of explainability. So Deutsche Fußball-Liga is the organizer and marketer of Germany's top soccer leagues, such as Bundesliga. And they wanted to enhance the kind of fan viewer experience. And so they built the so-called Bundesliga match facts, where as somebody is watching the game, we can provide some additional interesting probabilities, such as the system predicting the likelihood of a goal being scored from a particular game situation. So let me show you a quick video that explains exactly what this is, and we'll talk about some details of that in a moment.
Expected goals, or X-goals, help to calculate the likelihood of scoring for each shot in the game. The machine learning algorithm was trained by analysing more than 40,000 shots on goal and can precisely determine the goal probability of all different kinds of shots. The calculation considers the distance and angle to the goal, pressure from opposition defenders, and the goalkeeper's position. The speed of the player at the moment he shoots is also crucial, as is the question of whether it's a shot or header. A special case and example alike, the penalty kick. Here the goal probability is 77%. Each case is unique, but expected goals allows every chance to be objectively evaluated. In this example, Robert Lewandowski's pass increases the goal probability considerably because Thiago has a clear shot on goal and is standing centrally.
Oh, how easy did they make that look?
The goal probability therefore refers to a very specific shot. X goals, on the other hand, is the sum of several goal probabilities. This makes it possible to calculate a player or a team's possible goals in a match, which allows the efficiency to be newly evaluated.
Well, that was exciting, huh? In fact, a lot of details of the system and the approach can be found by scanning this QR code and reading the blog post, the link to which I also provide down below. So now that you've watched the video, you understand what these different features are. Right, so for example, angle to goal, the smaller the angle, the harder it is to score, because the goal opening is very narrow, and the wider the angle, the easier it is to score. So perhaps it's no wonder that in terms of the SHAP algorithm and the corresponding SHAP values that are computed, angle to goal is actually the most important feature overall. So what we're seeing here is the so-called global explanation, where we just look at the model at the aggregate and saying that in general, the angle to goal seems to be the dominant feature that influences the ultimate prediction of goal being scored. And of course, distance to goal is the second, and all the other ones here that you see. Now, these general or global explanations are important because that gives us some insight as to how the model functions, but we also want to see the so-called local explainability, where for any given prediction, we would like to understand what are the factors that actually contributed to that specific prediction for this game situation. And what you see on your screen is the typical graph for SHAP values, and it's a little bit hard to interpret at first, so let me explain what you're seeing. So first of all, if we look at a particular attribute, such as angle to goal at the top, well, it looks like there's a bunch of dots displayed there, and indeed, these are the values, or the SHAP values, for this particular attribute for all the different data points or gaming situations that were analyzed. Now, what about the colors? So you see that some of these dots are red, others are blue, and then various shades in between. Well, this is shown kind of on the right. It gives you a sense of what is the corresponding value of that feature. So the higher the angle to goal, which means the scoring kind of angle, or the view of the goal is very big, so there's it's easier to score. The redder the dot that you see, and conversely, if the dot is blue, as is on the extreme kind of left at the top of this graph, it means that the angle was actually very small, very narrow, so it's harder to score. Okay, so then if we look at the actual Shapley values based on the horizontal axis, we could see that the red dots, which correspond to higher angles, larger angles to goal, relate to the higher values of SHAP, or higher SHAP values. And that makes sense, because what we're saying is, what this explanation is telling you, is that the higher the angle, the more important that feature becomes in determining whether the goal will be scored or not. And if the angle is small, such as in case of blue points, then it seems like this stops being the most important feature in terms of its correlation with the ability to score the goal. So we could look at others here where the exact opposite situation occurs. So for example, the distance to goal, right? If the distance is large, which means the dots are red, then it's not influencing the goal likelihood. But at the same time, if the distance is very small, which is blue, and the points are aggregating on the right, the Shapley values are higher, right? And that tells us the story about this becoming a much more important attribute as you're getting closer and closer to the goal. Anyways, this is also an aggregate picture, but there is a way to look at just the individual prediction and see which factors are influencing it and to what degree. Now, another example that we typically see explainability being needed for is churn prediction. So here we're trying to predict whether a customer is about to stop using a service or a product of a particular company. And again, in this data set, I don't want to go into the details here, but this is about marketing emails. So the first top two attributes are about emails being sent and how likely is that email to be opened by the recipient. And all of these are different factors that will then help us understand why a particular churn prediction is made. And you can see how and why it's important. If we're going to mitigate churn in some way, we need to figure out why the customer is about to leave our services. It could be that it costs more than the customer is willing to tolerate. Well, perhaps there's a way to move the customer to a lower subscription tier, for example. Or if the customer is not really engaged, let's say it's a content provider and the content doesn't seem to be engaging enough for the customer, perhaps the mitigation technique would say, well, you need to highlight the content that you do have or we do have that is relevant to the customer. So better kind of recommendations and discovery. So here is one specific example. Capcom is a video game company out of Japan, and they actually used SageMaker Clarify to explain their churn prediction model. And here are some additional details. Every company, of course, has a slightly different type of product or service, and therefore you need to define what it means for somebody to churn. And in their case, what they're looking at is they're looking at the past 7 days and the interactions and engagement of a user with this game. And based on looking at the last 7 days, they're able to predict what will happen in the next 7 days. And the way they define churn is that if that user basically out of those 7 days logged into the game less than 3 days, then it effectively means for them that the customer is churned. And given that definition of churn, they were able to predict this with an amazing 94% of accuracy. Quite impressive. All right, so we talked about explainability based on tabular data, which means numeric and categorical data as input features. But what about other modalities, right? Text and images. So in fact, if you scan the QR codes, you'll land on the Jupyter notebooks that give you step-by-step instructions of how to apply the same approach and kernel SHAP algorithm with SageMaker Clarify on text and on images. There's another notebook that I'm not showing here about not just image classification, but actual object detection. And yeah, so let's look at some specifics here. So first of all, we'd look at text. So suppose somebody built a model to classify reviews for an e-commerce products. So we'd like to assess if this review was positive or negative, or maybe neutral. And given the prediction and saying that this review looks positive, we would like to know why that is. And one way to do it, of course, is to treat the input text in terms of words, phrases, or entire sentences as those input features. And then we want to know, well, which of these sentences or which of these phrases contributed and in which direction, right? So we're computing those same SHAP values over the text. And what you can see here is, okay, so I love this dress. Well, this clearly is positively influencing the overall sentiment of this review. And so it's highlighted here in a darker green color. And then at the same time, on the other review, it says there is no stretch at all with the materials, and no wonder that this is assessed to be negatively influencing the sentiment of this piece of text. All right, well, let's actually look at the details. And so we'll jump into a SageMaker Clarify demo to see how this model is built and that explanation is obtained. So in this demo, I've opened up SageMaker Studio and a specific Jupyter notebook called Text Explainability. This is the one that was shown a QR code for, and so you can get here and replicate exactly what I'm doing here. I've already run all the cells, and I just want to highlight that I'm using the Python 3 kernel. So we'll skip some of the preliminaries. In here, we load the data set, and as was already mentioned, the data set is related to e-commerce and women's clothing reviews. So if we look at the actual fields here, we see the review text as one of the key fields that we will use. What about the labels for the sentiment? Well, instead of the sentiment, we actually have a rating here. And the reviews are rated from 1 to 5 stars. So we're going to have to create a notion of sentiment based on the ratings. And so we will make an assumption that if you have the rating of 4 and above, that's seen as positive sentiment. If the rating is 2 and below, that's negative. And if the rating is exactly 3, then we take it to mean neutral. And so we'll do some pre-processing here to do exactly that. In this data set, we have 23,000 rows and 10 columns all told. So as usual, we will need to split into train, test, and validation. And now we're ready to build an estimator. In this case, we're going to use a Hugging Face estimator and the Dilbert base uncased model. This is all specified in the hyperparameters. Of course, we need to specify an instance type, which we'll use for training, and some additional parameters, including the training and test data sets. Once the model is trained, we will need to deploy that model, and that's done in a standard fashion over here. We will need to choose an instance type for the deployment as well. And so far, this is not very different from what you would normally do with SageMaker and training the model. Once the model is deployed, we can test it. So here are some sample reviews that were picked. Some of them are positive, others are negative. And we could see that if we run this against the endpoint, we get the predictions. And obviously, the higher the value to 1, that means the more positive the review is. And then if it's close to 0, it's actually seen as a negative in sentiment. So finally, we're ready to run explainability here. And for that, we're going to need to provide some additional configurations. But first, we're going to pick a few samples. And in this case, we're just going to pick 10 reviews. We pick them to be of longer length just because we're going to use the granularity of a sentence. So we need multiple sentences in there to be able to see which ones contribute to the ultimate decision. Let's look at the configuration here. We define a SageMaker clarified processor. It's going to run a SageMaker processing job. We need to specify a type of instance that will be used for running this job. We will, in the process of running this job, SageMaker will also create a temporary model endpoint, and we need to supply the specific instance here, of course, the model name and some additional parameters. But with respect to the configuration on the data, we need to provide the input and output for where the explainability results are to be written, and then clue in SageMaker clarify of the relevant text column for which to grab the respective features, and then looking at some additional config of SHAP. Remember the baseline? Well, what do we do with missing features, right? Because we're going to take that review and eliminate some of the sentences out there. So we will be replacing these sentences with a special token called unknown. We will choose 1,000 samples for the estimation of true Shapley values, and then we'll use mean absolute value for the aggregation. And of course, we see sentence and we see language chosen. In fact, SHAP can support 62 languages and can handle text, which includes multiple languages, in fact. And so we run the explainability here with the SageMaker clarified processor that will kick off the job. And once the job runs, we effectively obtain the explanations and are ready to visualize them now. Now, just to look at one of them, here is an explanation that's shown on the screen. So we see that here is a sentence, and its attribution is fairly low. We can find a sentence with a much higher attribution. So the Shapley value here is higher. I love this dress, and that makes sense. And similarly for other sentences in this review. So this raw output is great. You could understand a lot of detail, and it's useful for debugging. But of course, we want to get to visualization that I've shown. And for this, we're going to use a Captum library for highlighting the text. And with details of the actual function and how it's built is probably not super important. You can always examine it at your own time. But in the result, in the end, we get to this visualization, a portion of which you've already seen. So we can see that the model predicted a particular sentiment, and here's the true label, and we could then analyze the explanation, understand that out of all the sentences, these contributed to the positive result. These affected the model to lean it more towards the negative. And in the end, the overall kind of confidence, you could say, or the overall prediction value is 0.84, which is ultimately seen to be positive overall. Let's move back to the regular presentation at this point. All right. Well, hopefully this was educational. And now we would like to look at how to apply the same SHAP algorithm to computer vision. So you could see the image here of a pug wrapped into a blanket or a scarf. And let's say this model is actually predicting for this image to contain a pug. Well, what are the features of the image? These would actually be the raw pixels that of which this image is composed, but it would be silly to try to compute the marginal contributions of each pixel. You could see that potentially there's lots of noise, or there's lots of pixels that are really irrelevant to the ultimate decision. And so instead, what we're doing is first building the so-called superpixels. And we use an algorithm called SLIC, or simple linear iterative clustering. And it will try to carve out certain segments out of the image that appear to be coherent in some sense, or likely belonging to the same depicted object or background in a semantic sense. We'll see some details shortly, but imagine that the face of the pug is determined to be one such superpixel. Well, if we remove this from the input to the algorithm, and so our coalition is basically missing that particular superpixel, it's likely that the prediction will change, right? It's likely that the algorithm will not see a bug in this case. And we will then know that that particular superpixel played a crucial role in such a prediction. So let's look at another example. Imagine that you have an algorithm that predicted that this is a pyramid with the confidence of 63%. And now you'd like to analyze this for explainability. You'd like to understand why this prediction was made. So the first step is to use that SLIC algorithm to compute these superpixels or segments in the image. And we can specify some parameters, such as the number of these superpixels that are being generated, plus some additional ones. And let's assume these are the segments that the algorithm chose. Well, then what we're going to do is create lots and lots of synthetic images. And you can specify how many such synthetic images or samples you need to provide. Because remember, kernel SHAP is estimating the attributions, and it's not going to create all possible combinations of these superpixels, but will use a subset of these. And then in each of these synthetic images, it will replace some of the superpixels with random noise. So here's an example, right? It's a coalition of sorts where we've eliminated some of the superpixels. And we're now going to feed all such images into the machine learning model and obtain the predictions. And depending on how the ultimate prediction and confidence of this still being seen as a pyramid, we will be able to, on aggregate, compute the Shapley values. And in this case, the result is shown in the form of a heat map, where the darker the particular region is, or the particular superpixel is, the higher the SHAP value of it is, and therefore its contribution or attribution to the overall decision. And in this case, you can kind of see that the sides of the pyramid contribute the most, and that does match our intuition as well about why this is seen as a pyramid. So as a result of this explanation, you could say that our trust in the model has increased in the process. But I'd like to show you another interesting example from the literature, just to see and reinforce why such explanations are useful. So this is taken from a paper on Lime, which is a related technique to SHAP. And there they've applied it to a model that was attempting to predict and determine whether an image has a husky or a wolf in it. Of course, animals are similar looking to some folks. And so after having built the model, they've produced an explanation, especially if we look at the image shown. Well, here the husky was classified as wolf. So why is that? And when we look at the explanation, it turns out that the model is actually not looking at the animal itself. You could see that the parts of the image that it zeroed in on show snow and some other background. So in fact, what they've discovered is that it just so happened that in a lot of training images with wolves, they were, at the backdrop of snow, or they had snow in the background. Just so happened that that's how their training set was built. And as a result, the model is actually focusing on the snow, just looking at snow. And if the snow is present, then the prediction is wolf, and not it's a husky. So a bit silly, but you could see that after such an explanation and analyzing maybe several images like that, you will realize that actually this model is not so great. You could say it's buggy, and therefore one would need to approach it differently, perhaps obtain more images where wolves are not with snow in the background, and maybe have more huskies with snow in the background. But we need to mitigate this somehow and approach it differently. Cool. So in summary, we've looked at what responsible AI is, and hopefully you've learned about it. You've learned why explainability is needed and how it's done in principle with the SHAP algorithm, and how specifically SageMaker Clarify helps you there. And at this point, if you want to go further, here is a set of links that you can follow, and you get a lot of resources around the topics of responsible AI. So the first one includes some ultimate links to the tooling as well. The second link covers research articles on the topic, and we have published over 400 such articles on responsible AI. And the last two are specific to SageMaker Clarify, developer guide, and the product webpage with various additional materials. So at this point, I encourage you to take this tool and apply it to your own models and your own data sets. And that concludes my talk. Thanks for listening. And if there are any questions, we will attempt to answer them now.
Thank you to our speaker and our moderators for their time. On your screen, you will see a few live poll questions. Please enter your feedback by hitting the radio button next to reply for each poll and typing in any feedback. And with that, we're going to go ahead and end today's webinar. I want to extend a generous thank you to our speaker for their time and a great presentation, and to our moderators for answering the audience questions. If you have any comments on our previous and upcoming webinars, please feel free to email us at aws-webcasts@amazon.com. Your feedback will help us to improve our webinar programming. Thank you for taking the time to join us today. Please enjoy the rest of your day.